Hello, I'm Professor Ryan, Department of Mechanical Engineering, Vimaljyothi Engineering College, Chamberi, Kannur. I welcome all of you to this course on refrigeration and air conditioning. In this lecture, we will see Cascade Refrigeration System. The term cascade means waterfall. In Cascade Refrigeration System, two different freezing circuits are used which uses two different refrigerants, and this will be connected by using a heat exchanger. Need for cascade system. If a single stage system is used with refrigerant having high boiling point, then extremely low pressure in the evaporator is required with large suction volume. If a single stage system is used with the refrigerant having low boiling point, then extremely high pressure in the condenser is required. If a single stage system is used, then pressure ratio will be high, so coefficient of performance will be low. Now in cascade system, we will be using two different circuits. One is high temperature circuit and another one is a low temperature circuit. The refrigerants used are in high temperature circuit, we will be using the refrigerants like R12, R22, then ammonia, R404A, R134A. Whereas in low temperature circuit, we will be using the refrigerants like carbon dioxide, R13 and R23. Now this is a typical cascade system. You have a higher temperature circuit and a lower temperature circuit, and these two will be connected by using a condenser. That is, evaporator of the higher temperature circuit will be connected to the condenser of the lower temperature circuit, and by in terms of heat exchanger. That means there is a heat exchange between this condenser and this evaporator. Heat from this condenser is rejected into the heat from the heat of this evaporator. That is, the heat from the lower temperature circuit, lower temperature circuit is rejected to the evaporator of the higher temperature circuit in terms of the condenser. Okay, so before starting, first we have to switch on the higher temperature side. That is, this is higher temperature side. This compressor is to be first switch on, so that the vapor which is present here will be sucked by this compressor, and then it is compressed to higher pressure and higher temperature, and that higher pressure higher temperature refrigerant passes through the condenser of that circuit, and where it rejects the latent heat, and then a liquid refrigerant is formed here. And then when that liquid refrigerant expands through the expansion valve, a lower temperature liquid refrigerant is attained here. And when that low temperature liquid refrigerant passes through the evaporator coil like this, it absorbs the heat from this space and gets vaporized, whereas the temperature of this space reduces. Now, once the after a few minutes, the temperature in this heat exchanger will be very low, maybe around -5 to -10 degrees Celsius. Once we attain that temperature, that is around -5 to -10 degrees Celsius, then we switch on the second system also, so that which uses a separate refrigerant. Okay, so that refrigerant vapor will be sucked by this refrigerant, and then it is compressed by this compressor, where then it is high pressure refrigerant enters into this condenser, where it rejects the latent heat to this evaporator. Okay, and that refrigerant condenses. That condensed refrigerant expands through the expansion valve, and lower temperature, very low temperature, lower pressure refrigerant is attained here. That lower temperature, very low temperature refrigerant passes through the evaporator. It absorbs the heat from this space to be cooled and gets vaporized like this, and then it is sucked by the compressor. So that means a higher temperature circuit continuously works, and lower temperature circuit also continuously works, so that heat from this space is rejected by this circuit to the evaporator here, and that heat will be rejected by this second circuit in terms of this condenser like this. So that means this heat from here is rejected to the outside. So here we will be getting, here inside this first heat exchanger, we will be getting a temperature around -10 degrees Celsius, whereas here we can attain a temperature like -70 to -100 degrees Celsius. Now, coefficient of performance. Now if you see the TS diagram and the pH diagram, See, in TS diagram of, this is the TS diagram of the higher temperature circuit, and this is the TS diagram of the lower temperature circuit, and you can see a small temperature difference is required here. That is the condenser of the lower temperature. The temperature of the condenser side of the lower temperature should be slightly more than that of the evaporator of the higher temperature side, so that then only heat will flow from here to here. So this is the pH diagram corresponding to this TS diagram. So this is the first circuit, that is 1 2 lower temperature circuit, that is 1 2 3 4 is the cycle, and higher temperature we have 5 6 7 8. Now if you see the coefficient of performance of the higher temperature side will be that refrigeration effect divided by compressor work input, that is H5 minus H8 divided by H6 minus H5. Now if you see the coefficient of performance of the lower temperature side, the cycle, so we have refrigeration effect will be H1 minus H4 divided by H1 minus H2 minus H1. So that is the coefficient of performance of the lower temperature side. If you see the overall coefficient of performance, we have to consider this. Here is the heat suction, okay, whereas the work input will be here and here. So you have two compressors, we have to drive two compressors, and here this heat will be rejected outside. So this is the refrigeration effect. That is, if M1 is the mass flow rate in the circuit, and if M2 is the mass flow rate in the higher temperature side, that is M1 is the mass flow rate in the lower temperature side and M2 is the mass flow rate in the higher temperature side, then overall coefficient of performance will be M1 into that refrigerant effect, that is M1 into H1 minus H4 divided by M1 into H2 minus H1 plus M2 into H6 minus H5. We have two compressors, you have to drive two compressors. So here this is the refrigerant effect, and you have work input to this compressor and this compressor we have to consider. Now applications. Cascade refrigerant systems are commonly used in the gas liquefying plants. Now like in petroleum gases and industrial gases. Another application is in the manufacturing of dry ice. Also it is used for deep freezing. Now advantages of cascade system. Since each cascade uses different refrigerants, it's possible to select a refrigerant that is best suited for that particular temperature range, and high or low pressure can be avoided. Now another advantage of this system is that if we use two compressors in series with using a single refrigerant, that is the discharge side of the lower pressure side is connected to the higher pressure side, suction side of the higher pressure side, then that is the compressors are in series, but we use the same refrigerant. In such a system, there is a chance that there's a chance of migration of lubricating oil from lower compressor to higher compressor, so that can be avoided. Hope you got some basic idea about the working of cascade system and its TS and pH diagram and its advantages. Thank you very much for listening to this lecture.